Wir starten? Good. So I will switch to English. Hello everybody, good to have you here. My name is Frederik Berstecher, I'm from TDK-Micronas, and I will give you some insights into the e-motor position measurement, and we will have a closer look into the topic of angular accuracy under extremely difficult mechanical and electrical conditions. So there's quite a change in the market over the years. So starting in the 1960s, it was when the first electrical alternator has been standard equipment in production cars, so it's already quite some time ago. In the meantime, we're talking about much more electrical system in cars, which have mainly replaced mechanical and hydraulic systems, mainly due to higher efficiency, reliability, as well as higher safety. And such growth in electrical systems also pushes the concern about magnetic stray fields. Stray magnetic fields, they can be generated by any current carrying wire, by motors or magnets, which are used for other sensor systems. And the number and the strength of the stray field is bigger, especially in pure electric vehicles or hybrid electric vehicles. And this creates new challenges for the design of new sensor systems that are used in EVs as well as hybrid electric vehicles. The criticality, especially for magnetic position sensors, is that the accuracy of these sensors is negatively impacted by those stray fields, because normally magnetic position sensors, they shall measure magnetic fields. So this is for sure an issue. At the same time, ADAS, so advanced driver assistance systems, autonomous driving and increased function safety requirements, they demand a new kind of sensor with additional feature set and a sensor that offers higher availability. The importance of these market changes, they're underlined by two major standards which have been introduced in the market over the years. So one is ISO 26262, which is the function safety requirements. On the other side, we have the ISO 11458, which are requirements for EMC, especially magnetic disturbances. Having a short look at the target applications of TDK. So TDK is a quite big company, and we have several sensors in our portfolio. Especially the automotive demand is booming for magnetic sensors as well as smart actuators. This is mainly due to the case trend, which are mega trends in the automotive market. Especially the autonomous and electrification trend is driving the need for such kind of sensors. Especially electrification requires more magnetic position and current sensors, which are key parts to have an efficient management of motors as well as batteries. So these are key areas that you can see here, like drive, steer and stop. And for each area you can see there's a strong trend towards electrification, as well as to have by-wire systems. With the sensor which I would like to have a focus today on, we are mainly targeting for motor position measurement, and especially high-speed capability sensing is a key feature of the sensor. And the sensor we're talking about today is the Hall 32X sensor family. It's addressing especially the need for stray field immunity. So here we are going to address especially the stray field requirements which are introduced by the ISO standard regarding homogeneous stray fields. We have also here many diagnostics implemented to address highest safety requirements, and we do also follow here the ISO 262 compliant development. So here for the single die implementation, we are achieving ASIL-C ready with a single component, and this can be even equipped in systems up to ASIL-D as a single die sensor. Next to this, it was important for us that it's a sensor that is easy to use. So the sensor, they can easily replace XMR-based sensors or resolvers. So we're offering here sinus cosinus outputs, either as differential or a single-ended output. And they can be used for an external angular calculation by means of an arcus tangens calculation, for example, on ECU side. Another key aspect is simplicity as well as robustness. And here we have a setup which is quite simple. So the sensor is being used in an on-axis configuration in combination with a two-pole magnet, and it offers very high robustness against mechanical misalignments. And I will show later on how this really looks like when using it in a system, sensor system. Once again, so this is a typical application configuration. So you have here your electric motor, which can be a brushless DC motor, for example. And at the end of the shaft, you will place your two-pole magnet, which can be cheap ferrite material, for example. And we place here the sensor as a SMD package at the end of the shaft, and it's a single component. So it's a single placement. And we have two family members within the whole 32X family. So we have a variant which has 3 horizontal Hall plates, as well as a variant which has 6 horizontal Hall plates. And I will show later on the differences, especially in terms of system robustness. For both variants, they can support stray field immunity. So we do have here an intrinsic stray field robustness, which is already achieved on sensor level. So there's no need for external shielding, or there's no need for a stronger target magnet to optimize here the robustness. So this is not needed, and therefore it's very interesting to have a cost-efficient solution. As I described before, so we are offering sinus-cosinus outputs, means the A to D conversion as well as angle calculation has to be done on MCU side. Depending on your system accuracy requirements, you can apply some additional compensation, which can be done statically or dynamically. Dynamically is of interest for sure if you have very high accuracy requirements, because then you can optimize the resulting signals. For sure, the compensation can be done externally, but we do also have an integrated compensation feature in our device, which has the target to offload the ECU efforts. And so here we have the capability to optimize the gain mismatch of the sensors. So here on the right-hand side, we have an ideal sinus-cosinus output as well as non-ideal sinus-cosinus output. And there can be different error sources for this. I will show this later on. But the key message here on this slide is that we have already integrated feature set to compensate for these main errors which can be introduced. Now, having a closer look into the system level performance. So I was describing here the potential error sources that we can have when combining the magnetic position sensor on system level together with the magnet. For sure, we have sensor errors. There's no ideal sensor available on the market, but we do have a highly accurate sensor already available. So we have the capability to achieve an angle accuracy or angle errors less than 0.1 degrees after applying some very basic external dynamic compensation. With this performance level, you can almost address every kind of application with this small angular error. Another key aspect when looking at the sensor errors itself is the topic of speed capability and delay time. So in TDK-Micronas, we apply a production trimming for the bandwidth of our sensor, and this gives us the capability to achieve a very, very small delay time variation over temperature and lifetime, and therefore the resulting phase error at high speeds is very, very small. So we're talking here about less than 0.08 degrees. Let's have a look at stray metals. This can be also an error source, but this is not an issue for magnetic position sensors, so they are not affected. This is only an issue for inductive-based sensors. So this we don't have to consider at all. So it gives quite some flexibility for our sensor to integrate on the system level. Stray fields, I mentioned already, this can be an issue for magnetic position sensors, but how about Hall 32X? Let's have a closer look. Well, we have active stray field compensation. So it's not really an issue for our sensor, but let me show you some details here on this slide. So we're looking here at the stray fields, which are described by the ISO standard, ISO 11452. The ISO standard requires a DC magnetic field, DC field up to 4,000 amps per meter. So this corresponds to roughly 5 millitesla stray field at room temperature. The test procedure, according to the standard, asks to place the device under test in all 3 orthogonal directions and to find the most susceptible direction. And typically, the test setup is to use such kind of Helmholtz coil, which enable homogeneous stray fields. Now I'm showing the result when using a non-stray field robust sensor. Here, with a use field of 35 millitesla and a stray field of 5 millitesla, you would have increased angular errors up to 8.1 degrees. And this is for sure very, very critical, especially if you look into safety critical applications. Let's take electric power steering as an example. Here the safety goal is defined as maximum 5 degrees. So means we already exceed the safety goal definition. So there's absolutely no availability if you use a sensor which is not stray field robust. Let's have a look at the whole 3021, where we have characterization results. Well, it's almost not visible, so that's why I took a closer look here. So we are at the level of less than 0.1 degrees. And this, we even tested above the ISO standards. So we tested over the full temperature range from -40 up to 170 degrees junction temperature and after automotive stress tests. So means the stray field robustness is proven over temperature and lifetime, and therefore it enables a good efficiency for motor control over the whole lifetime of your electric machine. So we can put here a green mark. That's not an issue at all for our sensor, as the sensor family is robust against static as well as dynamic stray fields. What about mechanical tolerances? Well, mechanical tolerances, we have same conditions more or less for all type of sensor, magnetic, inductive or optical. But how about the whole 3021? We have a superior robustness against mechanical misalignments. Let me demonstrate you. So here we did a simulation. So we took a magnet with a diameter of 9 millimeters and a 4 millimeter height. It has been diametral magnetized, so it's a 2-pole magnet with a resonance of 1.22 Tesla, with a typical air gap of 2.5 millimeters. An air gap variation does not have a change on the accuracy of our sensor, it just have impact on the output amplitude of our sensor, since we are ratiometric. But we were checking for the main mechanical tolerances which can happen when you assemble the sensor together with the magnet. The different tolerances are shown here. So you can have a magnet tilt, you can have a magnet offset, some sensor tilting when placing the sensor on the PCB, and some sensor offset. These are really worst case tolerances. But we wanted to demonstrate the robustness of our sensor. We did the comparison between the 2 family members. So it's the whole 3020 and the whole 3021. The whole 3020 using 3 horizontal Hall plates. The whole 3021 is using 6 horizontal Hall plates. On the graph, you can see here on the y-axis the angular error, which results from the mechanical displacement. You can see here the different mechanical displacements which were checked. And the color coding shows the harmonic order, so which were derived from a FFT analysis. And this is described for the angular domain. You can see already, so we did the same task for both sensor types. You can see that the whole 3020 in general has a higher error level. And we also see here a third harmonic error, while the whole 3021 has in general a smaller error level, so below 0.15 for all mechanical tolerances. And what is very important is that the harmonic order, we're always talking about the 0th or maximum, the 2nd order harmonic, which is dominant. And those harmonic orders, they can be easily compensated by applying some very basic and simple compensation. So normally here, a 0 angle gain and offset compensation is sufficient to compensate for these main errors. Means there's no complex higher order compensation needed, which makes it very easy for the ECU to compensate and to achieve a very high performance level of our sensor. So we can put another green mark here, especially for the whole 3021, which is an extremely robust sensor solution. Having a short outlook, so the whole 3020, 3021, both are mass production ready. So PPAP is available, samples are available, all documentation is ready. So you can go ahead, use the sensor, design it in for your application. And to give you some outlook, we are also working on additional package variants, like a PCB-less package, to get rid of the PCB, and a full redundant version, which shall be available beginning of next year. To wrap up, the whole 32X sensor family is a solution which offers superior robustness against mechanical tolerances. This can help to reduce overall module assembly costs, because you could even go for wider tolerances in your production line. It simplifies in general the error compensation efforts, which can even be done on sensor level. So means you have even no external demands on ECU side. And thanks to the high robustness against mechanical misalignments, which can be statically as well as dynamically, so there can be a dynamic change over lifetime, means the motor commutation quality is given and ensured over full lifetime of your motor. Next to this, we have a robust solution against stray fields, static as well as dynamic stray fields. We do even overachieve the requirements from ISO 114528 without the need for external shielding or for stronger target magnets to reduce the impact, means the total cost is lower. Then we have the fact that we are robust or immune against stray metals. This also gives you as a designer more flexibility to design in our sensor, and it also ensures reliability over lifetime and a high quality. Then we have the topic of safety. We do have already integrated safety monitoring in our sensor. This increases the diagnostic coverage, enabling us to achieve ASIL-C with a single die sensor, and it also simplifies the external safety supervision on MCU side. Next topic, PCB-less. So this is related to my outlook that I provided. It's a major advantage compared to inductive sensors. You don't need a PCB anymore, and we offer a system in package. Means you can further reduce system costs because there's no PCB needed and no external components needed, because we have already the caps integrated into our package head. It also gives you more flexibility in terms of integration using the PCB-less TO package, and it's therefore suitable for very compact motor designs. Last but not least, simplicity and efficiency. So this is given by our solution because we can be combined with efficient and low-cost magnets like ferrite material. There's no need to redesign the sensing target because our sensor always works in combination with a two-pole magnet. So there's no need to adapt the sensing target according to your pole pair numbers of your electric machine. So there you have a straightforward solution which you can multiply to different kind of platforms. We can also support close air gaps, since we have here wide gain, which is programmable, so we can optimize the sensor to different mechanical constraints. And last but not least, low current consumption, which is also benefit compared to other technologies. So we're talking here about typically 10 milliamps, which is required for our sensor, which is in general a key item for our next generation vehicles, EVs, hybrid electric vehicles. That was it from my side. Please let me know if you have any questions. Feel free to step by. So we have a booth at 304 in Hall 1, so not so far away. We can have a more detailed discussion together. And yeah, I'm looking forward to have a chat with you. Thank you very much.